So let's start with this. So today, what I'm going to be talking about is the influence of oceans on boreal forests. So as you know, boreal forests, especially in North America and also in Asia, they are vast forested lands. Often they are surrounded by oceans. And what we're wondering in my lab is how these oceans play a role into conveying, producing, or transferring heat that is necessary for these forests to grow. Okay, so this is an example of a forest type in high boreal environments. It's massively dominated by black spruce lands with lichen on the ground growing. It's pretty homogeneous. It's almost always the same species that grows in most environments, either those that are very continental or even those that are more maritime. It's always the same. So it's a very simple and homogeneous landscape, which facilitates that kind of study that we want to establish today. So one thing that we know for sure, and we've been studying for a while, it's not to prove anymore that much. It's that boreal forest growth, so the biomass accumulation in these forests, is highly sensitive to summer temperatures. So there are other variables, there are other mixtures, but the most important always remains the summer temperature. Summer temperature is necessary for photosynthesis activation, and the assimilation rate also depends on the heat that is being transferred to the photosynthesis apparatus. So we can say that these forests actually grow more when summer temperatures are high. Okay, but one question that we rarely address is, where does that heat comes from? And most will say, well, it comes from the atmosphere. Which is right, but it also comes somehow from the oceans that surround the land, and these oceans act as conveyor belts to transfer some of the heat. And as you know, if we're taking as an example our region here, the Quebec-Labrador, that's where I live, that's where I do most of my studies. It is a landmass that is surrounded by many different oceans with different properties. So here we have the Labrador Sea, which is a very important, although very cold, water mass, which plays an important role in the overall oceanic circulation around the world. Well, it's a region where deep water forms, and this will influence a lot of the climatic variability around the world. But we also have the influence of southernmost air mass that comes from the Gulf Stream upwards up to our Quebec-Labrador Peninsula, right? But we also have air masses incoming from the west, which are not really influenced by oceans. So where does the heat comes from? It could come from the east, although if it's that, it should also bring some moisture, right? Because it's very cold air. These are very cold air masses. It could come from the southeast up to from the Atlantic Ocean, or it could come from the west. Although the west is somehow we expect the western air masses to be much more depleted. So here I present you our sampling protocol. We've sampled three different sites all along a gradient of continentality. And so we have a very continental site, which is Kaniapskau, which is right in the middle. It couldn't be more continental. It's really high elevation continental site. As you see in this map, we represent the Quebec-Labrador Peninsula with a very well-known continentality gradient, which is measured from temperatures, also from distance to coast. It's called the continentality gradient. And we depict the color here. So you clearly see that these two sites here, Keniepskou and Fairmount, they are pretty much continental, actually much more than than Goose Bay is. Goose Bay, it's not a purely maritime site, but it's a clearly ocean maritime driven forested landscapes. All of these sites, they're all dominated by black spruce. So it's always the same species. The altitude is equivalent. However, in these three sites, the source of the heat and the types of air mass, the incoming air mass bringing that heat is relatively different, with two sites being very continental and one site with a much more maritime climate. So the way we see things in our lab is that we take forests as recorders of the interactions between the water cycle and the carbon cycle. So, as you know, trees under the influence of heat, they assimilate the atmospheric carbon and they store it into the wood, right? But by doing so, they also evaporate water. So if they evaporate water, it means that they assimilate water, right? So here we have some precipitation falling onto the ground and getting transferred as soil water content, and then becoming uptaken as a soil water up to the leaves, where it contributes to photosynthesis and then gets transpired. Okay, so all of this cycle is really important, because one of the things that we will argue is that through this cycle here, especially the water cycle, this water cycle will be imprinted by the signature of different air masses. So, as you know, for a stable isotope analysis, one of the things is that when there is some so as we move around the water cycle, the stable isotopes from oxygen get depleted differentially depending on the stress and depending also on the source water. For example, here you get the carbon incoming to the stomata, but out of the stomata, when there's transpiration, there's a preferential evaporation of lighter isotopes, which will contribute to make the water into the leaf much more enriched. Okay, so this is fractionation of stable isotopes inside the leaf, but we also have a fractionation of source water that comes from just the source water being entering the tree, that bears the signature of the continentality. As you probably know, when you move away from the oceans, so this is just a caricatural diagram, but it looks a bit like that, although to a smaller scale. You get the signature of oxygen stable isotope of source water that is assimilated by forest, that gets depleted as we move away from maritime air masses, right? And when you're very close to air mass, you can get -2 per mil compared to a standard that is actually maritime water, seawater. And then as you move inland, the source water, the signature of the isotopes, gets depleted. So that's a very interesting aspect that we're going to study today a bit more, right? Because if you look at all the information that we have in these three sites, so it's either information from measurements that are very discontinuous, or it's information from models. So the way the global model that we have, that are isotope enabled, introduce the isotope signature along the land. What you see here is that when you move from the maritime land to the continental regions, you get a depletion in stable isotopes that is about 5 per mil. 5 per mil. It means that you have a heavier signal in Goose Bay, which is the maritime site. You get an intermediate signal in Fairmount, which is the midway site, and the most continental site here gets the lower value because the isotopes, the heavier isotopes, have fell earlier into their progress inland. So that's what we expect as a signature from the source precipitation. Now, a bit closer to the expertise in our lab, when we look at what's inside the black spruce and look inside the tree rings, and we look at in each site, what is the signature of the oxygen isotopes inside tree ring cellulose. So, as you understand, we have to cut the trees, make an analysis of the wood content of the oxygen in the wood in each of the rings, and then we get a series for Goose Bay, Fairmount, and Kanievsko. So what we see is we get exactly the same gradient, right? We get cellulose, part of the wood, that is heavier in Goose Bay, and that gets lighter as we move inland in Kanievsko. So the more you're inland, the more depleted in stable isotopes from oxygen you get. So that's a rather interesting aspect, which points to the fact that precipitation here has a signature that probably bears already a continentality signal. And when this precipitation falls into the soil and gets assimilated by the trees are imprinted by a precipitation signal that gets some imprint by the proximity to the coast. So it's quite. So this is a first striking results that I had to present today, but then we have to bring some nuance. Here I'm showing all of these three curves. So these were tree ring stable isotopes curves. And what we do with these curves is that we do daily correlation functions. So we look at how in one single year, the delta O18 curve correlates with the temperature of the maximum temperature along the continents. So what we see is that between day 120 to about day 250, so that's like spring and summer, we get during that period significant positive correlation, meaning that the source water and the tree ring cellulose are processes that are very sensitive to temperature. But what we see that is most important here is that the site in Goose Bay, so that's the more maritime site, starts to respond earlier than other sites, about a month earlier. And this underlines the fact that it's probably the spring conditions are probably very important for the interpretation of the maritime connection. So when you look at the spatial correlation of the delta O18 in tree ring cellulose series and the relationship with maximum temperature. So what you do is that you take each of the site, make a correlation with maximum temperature all across Canada. So what you see is that Kanievsko and Fairmount, they both have, they are both connected to, I would say, western air masses or southwest air masses. Look at Fairmount. It's pretty striking here. You really get a connection with, and this is only for Canada, but we could extrapolate this to the US, but it's really connected to air masses coming from the southwest and coming up to Fairmount. Okay, while in the east, we are kind of really connected to you see the red really gets redder as we get close to the coast. So we really get a signal here that is really more maritime, I would interpret. as we get closer to the Labrador Sea in Goose Bay. So I would interpret these patterns as being quite different in terms of connection or teleconnection with maximum temperature. Now, of course, now we start analyzing model, and I forgot to include the source here of the data used, but this is models. Okay, so what we interpret is that we interpret the inside the model, inside the Goddard Institute model, the NASA model, which is isotope enabled. We analyze the delta weighting signature of precipitation and the maximum temperature, and we look at how these spatial patterns evolve. And what we see is that in the spring, that's the period where it's the most sensitive, we clearly see here in the Labrador Sea that there is a strong connection between the precipitation signature of water and maximum temperature, and that it's really strong in the spring period, right? So I think that starting from now, we can start thinking that all points towards an evidence of the most maritime sites being more influenced by maritime conditions, and that maritime conditions change the signature of source water that are assimilated by black spruce. So as a conclusion, so the conclusions are preliminary, because this is preliminary work, but the main question that I asked earlier is, where does this heat come from? So actually, I've talked a lot about heat, but I've also spent a lot of time describing water and precipitation. So you might be lost a bit at that point. So I'm going to try to summarize a little. So what oxygen stable isotopes of precipitation water indicate is that the source water from the maritime air masses, they bear a unique isotopic signature with heavier ratios closer to the Labrador Sea and lighter ratios as we move inland. So all trees need water to grow, but the water that is assimilated closer to maritime sources has a different signature than those that are more continental. So this is an imprint from maritime connection. Then boreal trees, they will assimilate water, and their tree rings will be imprinted by the continentality gradient that is also visible in isotopic signature of source water. Okay, so it's not only affecting precipitation, it's integrated within the wood, and we can extract this afterwards. So we interpret this as the fact that ocean will transfer heat and moisture towards forested land, and that these transfers can be tracked down and will be proportional to the ratios of tree ring cellulose that is clearly driven by differential source water assimilated by the trees. And spring conditions seems to be of critical importance for heat and moisture transfers from Labrador Sea towards adjacent lands. This comes from the correlation analysis, which makes really a spring signal very strong. However, it's a bit soon for us to interpret all of this. We know that spring conditions may be very variable depending on sea ice content, how fast the water get open, or if they remain under ice for a long time period. We have to examine all of this, but we're pretty sure that depending on spring conditions, that the impact of oceans on surrounded forested lands will be very different. I would just like to thank all the sponsors that gave us money to perform this research.